hopefully this one with Ampere's law can be shorter because it's the same sort of structure as the Gauss's law one. So John Frensley, World's Finest Physics. I hope you've been watching these videos kind of in the sequence. So here's your super basic Ampere's law, straight wire, super long, find the magnetic field at P. We all know what we're supposed to do. We're supposed to take a loop. Remember, P has to be on the loop, just like P had to be on the Gaussian surface before. So that's my Ampere loop, right? And then we just, we say integral B dot dl equals mu naught I enclosed, right? Well, it's really B times 2 pi r becomes mu naught I. So B becomes famous mu naught I over 2 pi r, right? We're supposed to be able to do that quickly. But again, your students are just learning this first time. And really, after the tiniest amount of training, they can do this for this special case. But I want them to see how the flow chart works. So first thing we're going to do is we're going to select a loop here. It's going to be this loop right here. Shade in the length of the surface that contributes to the line integral. I don't know what it's called. What is this called? Because with Gauss's law, integral E dot d, this integral E dot dA, that's called flux, right? But I don't know what this is called, so I just call it line integral, right? Well, here, the magnetic field, okay, hold on a second. If the wire is coming out of the page, the magnetic field points all counterclockwise, right? So that means the whole line contributes to the line integral, right? So then B just becomes, and I need to label the radius, right? Integral B dot dl becomes B times 2 pi r. Again, it takes minimal training to do that. That's the easy part of Ampere's law. The tricky part of Ampere's law is the I enclosed. What is the loop enclosed? Here it's a discrete current, a current that can be counted, right? Okay, let's count the currents together. 1I. I wouldn't even put the 1, frankly. So, all right, that was a joke. So the B times 2 pi r, that's U, is equal to mu naught I, that's U. Okay, then there's B equals mu naught I over 2 pi r. Okay, that's a joke, right? All right, let's talk about it with a solenoid. This is the other one they might be asked to do on an AP Physics exam, is dealing with the solenoid. So now what I'm going to do is I'm going to choose a rectangle to be my my Ampere path. And students first, they want it to be the circle, and they want the circle to be like this. But then you have to tell them, well, first of all, you're not enclosing any current. Now, are you? And second of all, you are always traveling perpendicular to the B. If each of your little DL pieces are perpendicular to the B, then you're just integrating 0, 0, 0, 0, 0, 0, 0, because the dot product gives you 0 for perpendicular things. So 0 plus 0 plus 0 equals 0. Charge. You just found out 0 equals 0. Good job, genius. Okay, so what we're going to do is we're actually going to do this. You can enclose part of the turns. I personally choose to enclose all the turns. Okay, so that's my Ampere path right there. Okay, so that's the Ampere path right there, and it looks like its length is going to be called L. I'm going to call this length L. Now, which part of the path contributes to integral B dot dl? Not this piece, because here the little dl's go up, 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 but the B magnetic field goes out, out, out. That's perpendicular. So the dot product gives you nothing. Same thing here. Okay, the little dl's go down, 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 and the magnetic field points in, or into the solenoid. That's perpendicular, perpendicular, perpendicular. So it's 0, 0, 0, nothing. Now, the reality is that the magnetic field does go out and circle back around. The edge effects approximation that we make for a solenoid is that it's so long that the magnetic field outside is super weak compared to inside, so weak, the magnetic field outside is basically 0. That's the approximation we make. So there's no contribution to integral B dot dl here or here, because that is dl being perpendicular to B. None here, because the magnetic field is basically 0. So this is the only contribution to integral B dot dl, meaning integral B dot dl turns into B times L. Yay. Good news, everyone. It's still a discrete number of currents. It's still a countable number of currents. I. It says the number of turns is n. So the number of currents is n times I. So then we get B times L. Lowercase l. Lowercase l, lowercase, call it capital L if you want, but that could be inductance, so be careful. Mu naught I, the I encloses Ni. So your B is mu naught n I over L, which could be written as mu naught n over L times I. And then that could be called lowercase n, which is called turns per length. And this equation is on the AP Physics formula chart. This one is not on the AP Physics C formula chart. The students have to memorize it or know where it comes from Ampere's law. This one is on the AP Physics C formula chart. This one is on the AP Physics 2 formula chart, but then you're not doing Ampere's law in AP Physics 2 now, are you? Okay, this is called a toroid, and it turns out that a toroid is basically the circular version of this, if this is like the linear version. So I'm going to go through it really quickly. The Ampere path is just going to be this. I'm going to call it radius r. The actual magnetic field flows around like that, right? So it's basically like, and most inductors that are made industrially are made this way. Part of the reason is because then the magnetic field loops around on itself without escaping into the world. See, this magnetic field escapes into the world around it. Escapes into the world around it, right? But this magnetic field can be totally enclosed and not interfere with anything else around. Okay, well, look at this entire thing. This entire thing has magnetic field parallel to every single DL, 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 DL. So this in R radius R, this whole thing is going to contribute. So this becomes B times what length? 2 pi big R. Still discrete currents. It says it's, N turns, each carrying a current I. So still Ni. So now this is just B times 2 pi R equals mu naught Ni. So it's the same result, okay? These are actually the same result. These are the same result. It's just that, is it the length of the solenoid or is it the length of the solenoid around a circumference, right? Is it the length of the solenoid or is it the length of the solenoid around a circumference? So it's the same thing. Oh, now this is what you really want to hear about. You really want to hear about what happens if I'm inside of a wire, right? Notice I give the students little space to find out the magnetic field outside because that is a freaking joke. They should be able to do it in less than 3 lines, right? But what if you're inside? Again, I'm going to use a circle, and the magnetic field inside is just as much counterclockwise inside as it is outside. Why? Because if I draw a pink loop outside, this pink loop encloses out of the page current. So that must mean it's counterclockwise magnetic field. This green loop also encloses counterclockwise current. Out of the page current. So it also has to be counterclockwise magnetic field. So U, radius is going to be lowercase r. Big R is the radius of the wire. Lowercase r is the radius of my loop. That takes me out to point P. That's where I want to know what the magnetic field strength is. So the entire length is going to contribute, right? Okay, what does the loop enclose? Well, now it's different. Now it's a distributed current with uniform density. Now, every time it's going to be area. So it's not like Gauss's law was. Gauss's law, it said multiply density by enclosed geometry because the geometry could have been a length, an area, or a volume. With current, it can only be an area. 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 Did I say it can only be an area? It can only be an area. So multiply current density by enclosed area. So that means I enclosed is J, that's current density, times area enclosed, except not today because I don't have J as one of my letters. Or set up a ratio. I enclosed current over enclosed area. The enclosed area will be pi little r squared, okay? Now, the total current, I, that's total current, I is the whole thing, over the total area, pi big R squared by, and then you get I enclosed equals I little r squared over big R squared. Okay, so B times 2 pi lowercase r. By the way, it's worth mentioning to students at this point that on the left-hand side of Gauss or Ampere, the R will always be the variable R that moves with the point P. You will never put the capital R that defines the object itself onto the left-hand side. The integral B dot dl will always be, or integral E dot dA will always have an R in it that depends on the point P, not on the entire thing, right? Okay, mu naught, what's I enclosed? The total I, little r squared over big R squared, cancel. And so you get B equals I R over 2 pi R squared. Okay, now what is the charge density again? Uniformly distributed. So that means that the charge density, J, is a constant times R to the 0. you remember in the last video where I told you that the field is always one power higher than the density? The density is r to the 0 because it's a constant. What's one power higher than r to the 0? R to the 1. It's worth remembering. Okay, one more. This is the last one. Okay, I'm going to tell you right now that the magnetic field is going to be some bull crap r to the cubed. How do you know that already, Friendly? Because that's one power higher than the density. The density is r to the 2. The field could be electric or magnetic, doesn't matter, is going to be r to the cube, is going to be a third power. I just know that already. So I'm going to choose my little Ampere loop. Its radius is r. Okay, the entire loop, so it's going to be b times 2 pi r. Your kids are going to get sick of writing that. I don't care. Okay, the loop now encloses, oh boy, oh man, I got to go this way now. A distributed charge with non-uniform density. What's my area? Well, your area is either one of two things. It's either length times width or it's pi r squared. Well, today it's going to be pi r squared. Well, the differential, the derivative of that, 2 pi r, but it's an implicit derivative since I took a derivative of r, dr. Hey, do you remember when I said that this is the same as that? Well, it still is. Okay, so now let's talk about this. Plug this and the density function. Okay, so the I enclosed is integral current density. Oh my gosh, the light's still going off again. Always with the lights going off. I don't know how to fix that. It's after hours. J, what was the J again? Oh, there it is, CR squared. Let's make sure we see that. CR squared, that's the charge density I was given, times the dA, 2 pi r dr. Okay, and I'm going to go from 0 to little r. Again, that's just integrating that much of the current, right? So I enclosed equals 2 pi, and c can come out. Now I've got r cubed, integral from 0 to r dr. So the I enclosed is going to be 2 pi c r to the 4th, and then this will be over 4, 1/4 r to the 4th. That's how an integral works. So 1/4 r to the 4th, that 1/4 and that 2 is just going to become 1/2. Okay, so b times, you come back here, okay. B times 2 pi r, so that's the left-hand side, which is always pathetic and always a loser and always easy. Oh, I didn't mean to do that. Mu naught, and the I enclosed, 1/2. That was a Freudian slip. I was about to do a Q enclosed over epsilon naught, now wasn't I? Okay, 1/2 pi c r to the 4th, right? So the pi can cancel. The 2 is going to come underneath and make this 1/4. That's the 2.5 getting together. And then this r is going to nuke that r down to a third. So we're going to get 1/4 mu naught c r cubed. All right, so there you go. That's the story right there. All right, so those are my flow charts. At some point, I'd like to come up with a Biot-Savart flow chart for Biot-Savart's law, and maybe a flow chart for calculating the force on a wire that is curved in a magnetic field, or something where the force, you can't just use force equals ILB. All right, well, all right, if you want to see anything else, just let me know.